Last time we finished our business with um, Cartesian product and Cartesian power. So we consider such things as sets of ordered tuples. Say here we have the set of all ordered tuples of length n of elements A. And of particular interest, there were pairs, Cartesian square, and in general products of two Boolean sets. Excuse me, two sets. Let's recall that for every z is an element of such a product of A times B, if and only if there exists x and y, x from A and y from B, such that z is the ordered pair of these two sets. So the product of A and B is the set of all ordered pairs of elements from A and B. It is much like coordinates. It is much like coordinates. So in the case of coordinates in the plane, we have the product of R and R, the pairs of real numbers. So we have different such pairs which are routinely identified with plane points. But now we are interested in subsets of such products. Clearly we may have quite many such subsets, and every such subset has a special name. In fact, we have a collective name for all such subsets. So we say that R is a binary relation. Most often we shall omit this word binary. Is a binary relation. It is a binary relation between A and B, between two sets, if and only if this definition is really simple. If and only if R is a subset of A times B. So a binary relation is any subset of the Cartesian product. Any subset. So what do we have as examples? Clearly, the empty set is always a binary relation between any two sets. The Cartesian product of A and B is a binary relation between A and B. But we are mostly interested in intermediate cases. Okay, assume that say A equal 1, 2, 3 and B equal 2, 4, 5. What do we have? Which binary relations are possible? In general, A times B consists of how many pairs? How many pairs do we have in A times B? How many ordered pairs are possible? 9, exactly. 3 times 3, 9 pairs. But it is well possible that we may take just some of these pairs. Let R consist of, say, 1, 4, 2, 2, 2, 5, and say 3, 3, 4. That's all. So this is an example of a binary relation between A and B. Every binary relation, okay. For every binary relation, let us define two more sets. The set of its first coordinates, that is the first coordinates of whatever pair that belongs to our relation, and similarly, the set of all the second coordinates. By definition, the set of all first coordinates is known as the domain of our binary relation. So the domain that is the set of all the first coordinates. What is it? Formally, domain is a subset of A. You know, every first coordinate of a pair from R must belong to A. We know that if a pair X, Y belongs to A times B, we know that it is enough to state that X belongs to A and Y belongs to B. So we proved this fact. We proved this fact last time. So if XY belongs to A times B, then X necessarily belongs to A. Why is it so? Because there is only one way to obtain the first coordinate from a pair. So it is a subset of A, the set of all such elements from A, which are first coordinates of at least one pair. How can I formulate this fact? How can I render it symbolically that X is the first coordinate of at least one pair? So the most obvious idea here is as follows. Let me say that there exists a pair from R where X is its first coordinate. But I can put it another way. There exists Y. There exists something such that a pair whose first coordinate, or better, the pair whose first coordinate is X and whose second coordinate is Y, belongs to R. So our domain is a set of all such elements from A for which a pair exists, or a counterpart Y exists, such that there is a pair XY belonging to R. Is this idea clear?
Yes.
Quite similarly, I can define the range. The range of R, that is the set of second coordinates. The set of second coordinates, what is it? Clearly, it is a subset of B. Let us take all such elements from B for which there exists X, such that X and Y belongs to R. Is it clear? Both the sets are clearly obtained using our second set construction principle. So these sets are legitimate. And if we come back to our example, what is the domain of this particular R? What is it? What is the domain here? The set of all first coordinates.
1, 2, 3.
1, what?
2 and 3.
2, 3.
2 and 3, okay, exactly. every such a number belongs to the domain. Why? Say why 1 belongs to the domain? Because there exists something, namely 4, because it follows from the fact that 1, 4 belongs to R, so there exists some Y, namely 4, such that 1, 4 belongs to R. Hence, 1 belongs to the domain. Okay, and what is the range? What is the range of the set of all the second coordinates?
2, 4, 5.
2, 4, 5.
4, 5. Yeah, or in the order of the appearance, 4, 2, 5. So we have obtained these two sets. Is it clear?
Yes.
Sometimes it is beneficial to consider the so-called field of the relation R. This field is just the union of its domain and its range. So these are exactly all such elements, all such sets, which are either first or second coordinates of at least one pair from R. Aha! Okay. One more example. You know, we had interpreted the plane as the product of R and R, the Cartesian square of real numbers. So it is our interpretation for the plane. Hence, every plane point is an ordered pair of two coordinates. And in fact, every set, every geometrical figure, every set in the plane is a binary relation. So RF is a binary relation. Between R and R. So, but what does it mean? What does its domain and range are? So consider some set F, some geometric figure, a subset of the plane. What is its domain? Its domain is a set of all such axes, first coordinates, the set of all such axes for which at least one y exists, such that x y belongs to F. Is it clear?
Yes.
So here we have our range, our domain. What is a domain? It is the same as the projection of F to the axis of abscess. Is this idea clear?
Yes.
Similarly here, here we have our range, that is the projection of our set to the ordinate axis. Is this idea clear?
Yes.
Okay. Our next point is the so-called diagram of a binary relation. Relation diagrams. I'm not going to define them formally, because formally these diagrams are almost the same as the relations themselves. But I want to give you the main idea of this diagram. What is a diagram? The diagram is a vivid way to depict our relation. Let us take all the points from A times B, excuse me, all the elements from A union B, or maybe all the elements from this relation set. So what do we have here? What is the field here in our example? Which points are either first or second coordinates of a pair from our relation? Let us take the union of these two. What is it?
1, 2, 3, 4, 5.
Exactly. So let us put some points, take some points in the plane, and label them with these elements 1, 2, 3, 4, 5 with a set. So 1, 2, 3, 4, 5. And now my next step will be to connect 1 to 4 with an arrow. This arrow is directed from 1 to 4, from this first coordinate to the second one. And this arrow depicts our pair 1, 4. Let us reproduce the definition of R. It consists of the following pairs: 1, 4, 2, 2, 2, 5, 1, 4, 2, 2, 2, 5. What else? 2, 5, 3, 4. So then I shall depict 2, 2, this pair, as an arrow. But here for this arrow, its beginning point coincides with its ending point. So this arrow is just a loop. Is it clear?
Yes.
Then next pair, 2, 5. I shall draw an arrow from 2 to 5. And the last one, what should I draw next?
3, 4.
An arrow from 3 to 4.
An arrow from 3 to 4. So this is a quick and easy way to visualize a binary relation. Is it clear?
Yes.
What is the domain? The domain is a set of all such points where from an arrow goes. And what is the range? The range is a set of all such points where to an arrow comes. Is it clear?
Yes.
So we connect x and y with an arrow, and sometimes, especially if we have more than one relation to show, sometimes we label our arrows with the relation name. We draw such an arrow if and only if the pair x, y belongs to R. There is another interesting way to denote this fact that xy belongs to R. We may denote it this way: x, R, y. This is the same. By definition, we shall write X ry if and only if xy belongs to R. So it is a kind of predicate style. So xy belongs to R. That means that the pair x y satisfies a binary property, a binary predicate, binary relation R, or you may put it the following way: X relates, in the sense of R, X relates to Y. Is it clear?
Yes.
And in fact, every binary predicate can be interpreted as a binary relation. Of course, if it is over elements of some set. Every binary predicate over elements of some set may be interpreted, may be treated as a binary relation. Okay, another example. Do you know the relation less than over the set of naturals? I hope you are familiar quite well with this binary predicate, less than, yeah?
Yes.
2 is less than 3. Is it true or false? After
True.
all, it is a statement. Is it true or false?
True.
So this one is a true statement. 5 is less than 5. Is it a statement?
No.
Why not? Why isn't it a statement? Clearly it is, but it is false. So this one is a false statement. Do you agree?
Yes.
But according to this notation, we can reinterpret it in terms of binary relations. We may say that x less than y means that x, y, a pair of natural numbers belongs to this binary relation less than. We can identify the predicate with the binary relation. So it is a binary relation. It is a binary relation between n and n over the set of natural numbers between n and n. So this is the set of all such pairs x, y, or beta. Let us rename the variables of a, b from n times n, where a is less than b. Is this idea clear?
Yes.
You can seamlessly identify predicates, binary predicates with binary relations. The only necessary precondition to do so is that your predicate is over elements of some identifiable set. Say here we have set, or the set of all natural numbers. Is it clear?
Yes.
Yes.
So now effectively we can treat every binary predicate, almost every, that is, over the set every. We can treat a binary predicate as a binary relation, as a set. So we can apply set theoretic operations. We can apply set theoretic operations to this former predicate, that is, to our newly obtained set of pairs. Okay, as an example, we can easily treat the identity relation, the identity predicate, that is, of being equal, x being equal to y, as a set. So by definition, this set is known as the identity relation. Okay, let A be whatever set. Then the following set, the set of all such pairs where the first coordinate coincides with the second one. The set of all such pairs is known as the identity relation of A. Identity relation. It is a set of all identical pairs. Is this idea clear? Obviously, the identity relation is a relation between A and A. By the way, by definition, we say that R is a binary relation over A or on A. Let it be on A binary relation on A, if and only if R is a binary relation between A and A itself. Is this idea clear?
Yes.
As an example, let us explore the identity relation of the following set. Let A consist of 2, 5, and 9. What is the identity relation of this set? Please tell me, how many pairs does it have?
6.
Really? Please name them.
2, 2, 2, 5,
Why
2,
2,
9.
5? Why 2, 5? Look, here we have two identical elements, x and x.
So only we can put identical ones.
What do you mean?
So we can only choose identical element, the element in itself, only that.
Yes. So how many do we have?
3.
Exactly. 2, 2, 5, 5, and the last one?
9, 9.
And how does the diagram look like? What is a diagram of the identity relation? It consists of loops. We have a loop at every point. Is this idea clear?
Yes.
This identical relation is simple, but it is quite important. It is quite important for algebraical operations over binary relations. And after these preliminary examples, after this series of preliminary examples, let us introduce two specific operations over binary relations. Of course, a binary relation is a set, so you may easily apply all known set theoretic operations to binary relations. After all, let us consider an example. So let P consists of 1, 2, say 5, 3, what else? I don't know. 2, 2. And let Q consists of 5, 3, 2, 1, 7, 9. Clearly, they are binary relations between some sets. For example, their range, their respective domains and ranges. But, okay, what is P intersection Q? Is it a binary relation? Clearly, it is. The set of common pairs. Please name those common pairs.
5, 3.
Anything else?
No.
No. But anyway, it is another binary relation. Likewise, I can consider the union of these two relations. What is it?
All of the elements.
Namely, 1, 2, 5, 3.
5, 3, 2, 2.
What
5,
else?
3.
5, 3 has
2,
been
1,
already
7,
named. 2, 1, 7, 9.
7, 9.
Or we can consider the difference, even the difference, P minus Q. What is it? All elements from P which are absent from Q.
1, 2, and 2, 2.
Exactly. And also, it is possible to consider the complement of a binary relation. But, of course, in order to define a complement, we need some universe. So, if R is a binary relation between A and B, where this A and B were fixed, of course, this A and B with such a property are not unique. But assume that they have been fixed. So we have fixed them. Then we may define the complement. What is the complement of R? We can define the complement of R the following way. All the pairs from A times B which do not belong to R. Is this idea clear?
Yes.
But these were our regular set theoretic operations. What about anything special for binary relations? Okay, let us introduce two more. Conversion. The first is known as conversion, and the result is known as the converse relation. Let R, as usual, be a binary relation between A and B. A binary relation. Then the converse, sometimes they say the inverse, but for some reason it is not good. It is better to call it the converse. The converse relation of R, or just the converse of R, is the following relation. Look, R to the power minus 1. Thus, it is denoted. So, R to the power minus 1, the converse of R, what is it? It is a set of all such pairs BA, of course, where, let it be BA, where B belongs to capital B and A belongs to capital A, such that AB belongs to R. So what is it? We have just changed the direction of every arrow in a diagram. Is this idea clear?
Yes.
Yes.
As usual, let us consider an example. So let R be, say, 3, 5, 7, 7, 7, 9, 2, 3, something like that. Aha. What is the converse of this relation? Name it. We should take
5,
every pair from R and change the order of coordinates there.
5, 3,
What else?
7, 7.
7, 7. Ah, look! Such a pair is invariant under the separation invariant. That means that it doesn't change. You change the order of coordinates in such a pair, but this pair is still equal to itself. What about this one? 7, 9?
9, 7. And 3, 2.
And 3, 2. And now let us look at the diagrams. So for R, we had something like that. 3, 5, 7, 9. So we had arrows from 3 to 5, a loop from 7 to 7, an arrow from 7 to 9, and from 2 to 3. Do you agree?
Yes.
These were our arrows for R. But what about the converse relation? For the converse relation, we can just change the direction of every arrow. Is it clear?
Yes.
But this arrow is intact, it is the same. From 7 to 7. Is this idea clear?
Yes.
Okay. As a corollary, let us explore what is the converse of the identical relation. The identity relation. What is the converse of it? It consists of all such pairs as 2, 2, 3, 3.
The identity itself.
Yes, it doesn't change. It doesn't change. As an exercise, you may prove that the domain of the converse relation equals, what do you think?
The range of the relation.
Exactly. And clearly the range of the converse of R is just the domain of R itself. Is this idea clear?
Yes.
A little more examples. What do we take, say, the converse of the empty relation? The empty set is a legitimate binary relation. Why not? What do we take no pair and then change the coordinates, swap the coordinates in every pair, in a no pair set? What the result? What will the result be? What is it?
The empty set itself also.
Exactly. What do we take A times B? The maximal binary relation between A and B, the set of all possible pairs. What is the converse relation?
B times A.
Exactly. B times A. More practical examples. Assume that we have our relation less than over naturals. So it is the set of all such pairs of naturals where x is less than. We assume that we know what it means to be less than. X is less than y. So say 2, 3 belongs to this set, and say 3, 2 does not. Does not, it is not the case, so it doesn't belong. Yeah. It doesn't belong. Aha! What is the converse relation? What is it?
Y is less than X. Or we say X is bigger than Y.
Exactly. The converse to less than is greater than. Exactly. X is belongs to this relation if and only if. So, by definition, that means that xy belongs to this relation. So, that means that yx belongs to this one. So, y is less than x, or conversely, x is greater than y. If we are interested in the way how x relates to y, x is greater than y. Is it clear?
Yes.
But what if we take the complement? The complement, it is the set of all such pairs of naturals where the first coordinate is not less than the second one. What is it? Look, xy belongs to the set if and only if for every x and y from n, if and only if x is not less than y. What does it mean?
So all Y bigger than X. Sorry, the
X
all
is
X bigger.
greater or equal than y.
Yeah.
Do you agree?
Yes.
If it is not less, then it is greater or equal. So that means that the complement is just greater or equal. Clearly, these are distinct. These are not the same, they are different. Hence, the complement and the converse are different things. Is this idea clear?
Yes.
And another operation more interesting is that of composition. Composition. It is a little bit trickier. What is the main idea? Let us look at a diagram. Assume that from x there is an arrow to y from relation P, that is, the pair xy belongs to P, and the pair yz belongs to Q. What does it mean? That means we may put it in words the following way. There is a path from x to z that consists of two arrows, first P and then Q. Is this idea clear?
Yes.
Okay. We may consider something like that. Assume that x, y, z are cities. Assume that these are cities. Assume that A, P, B. Assume that this means that B is accessible. It is accessible. It is accessible from A by air. You can travel by plane from A to B. Is this idea clear? It is a binary relation. Is it clear?
Yes.
Assume that Q means that AQB means that B is accessible. from A by, say, by bus. But how can we put the following idea? One can travel from A to B first by plane, then by bus. Say B. How can we put the following idea? B is accessible from A by traveling first by plane, then by bus. How can we put this idea into formal terms?
A Q dot P B.
What? A,
Yes. Then Q, small circle.
then
P
Q,
B.
but not Q. First we are traveling by plane. A, P, then something, then Q, then B. So here we have a change. Change point. Is this idea clear? So in mathematics, we may render it the following way. We may base our arguments on the following idea. Let us state that there exists such a change point. So what is it? We may say that AB belongs to. Okay, we shall define the following relation: P composition Q. Please look. Here P is written last. It is written last, but in this path it occurs first. So first we are going via P, then by Q, but in this composition symbol we are going to write P last. What is it? It is a set of all such pairs of the form AB where the first coordinate belongs to the domain of P and the last coordinate belongs to the range of Q, such that there exists C, there exists our change point, there exists C, such that, look, A, P, C, it is possible to get to C from A by P, and it is possible to get to B from C by Q. Is this idea clear?
Yes.
So what is the main idea? The main idea is that you can replace a path of two arrows, a two-arrow path, with one arrow, but this arrow belongs to the composition. So when taking composition, we are somehow generate a new relation. This new relation consists of one may say that it consists of pairs of arrows. Every two-arrow path where the ending point of the first arrow coincides with the starting point of the second arrow, every such a two-arrow path gives rise to one arrow labeled with our composition. Is this idea clear?
Yes.
But clearly we need some examples to really grasp this idea. Aha! So let P consists of the following pairs: 1, 2, 3, 4, 2, 3, 5, 1. And let Q consists of 2, 5, 4, 3, 1, 7. What is their composition? First of all, let us make a diagram, a joint diagram for these two relations. So we have 1, 2, 3, 4. What else? Which points do we need?
5 and 7.
5 and 7. Let us make P arrows black. So we have an arrow from 1 to 2, from 3 to 4, from 3 to 4, from 2 to 3. Look, we have a 3-arrow path, which results in 2 arrow paths. And from 5 to 1. Interesting. Is it clear?
Yes.
And what about Q? From 2 to 5, from 4 to 3, from 1 to 7. Is it clear?
Yes.
And now let us use green for composition. Where from? Okay, let us consider every point. Say 5. Where to can I get from 5 first by black, then by red arrow?
5, 1, 7.
From 5, I can get to 7. Is it clear?
Yes.
Look, we have 5 P 1 P1 Q Q7. So this is our change point. So there is a composition arrow from 5 to 7. Anything else?
3, 3.
No. From 5. Starting from 5.
No.
No. Let us look at 1. Where to can we get from 1 by a black arrow? To 2. Yeah. And by black, black and then red.
1, 5.
1, 5. Exactly. From 2.
Nowhere.
Nowhere. Of course, there is a black arrow leading from 2 to 3, but from 3 there is no red arrow. And what about 3?
3, 3.
3, 3. 4. Is there a black arrow outgoing from 4?
No.
No. What about 7? Is there a black arrow?
No, too.
No. So now we see that the composition is just what? 5, 7. What else?
1, 5.
1, 5. And 3,
And
3.
3, 3.
Is this idea clear?
Yes.
Yes.
Now let us prove some general properties. Let us prove some general properties, and then we may come back to more examples. Lemma 1. I say that for every binary relation P, I say that the converse of its converse is our relation itself. And the converse of the union of two relations is what? What is it? What do you think?
Q inverse of Q.
Converse, not
Sorry,
inverse.
yeah.
The converse of P, union or what? Or intersection?
Intersection.
No, of course it is union. Let us prove it. For the first one, what is the main idea? The main idea is to use characteristic properties when a pair belongs to this relation. Okay. Assume that, what does it mean? That xy, you know, every set is maybe uniquely expressed as an ordered pair. So there is no need to formally consider an arbitrary z. We can take an arbitrary pair for every pair, its coordinates are uniquely determined. So what does it mean that xy belongs to this set? By definition, that means that yx belongs to what? Change the order.
To P converse.
Exactly. But by the same definition, that means that
XY belongs to P.
Look, P and the double converse of P consist of the same pairs. Hence, they consist of the same elements. So these two sets are equal. Is this idea clear?
Yes.
And now let us consider the union. XY belongs to the converse of the union. Hence, YX belongs to what?
To P converse union Q
No.
converse.
No. I have changed the order.
Oh, sorry, yeah.
YX and XY.
Yeah, so P union Q.
But that means that either YX belongs to P, yeah? Okay, let me write it in full. Either YX belongs to P or the same pair YX belongs to Q. Do you agree?
Yes.
Now I can apply this conversion operation to both P and Q individually. So Yx belongs to P. This is equivalent to the following. Xy belongs to the converse of P. And likewise here, Xy belongs to the converse of Q. Do you agree?
Yes.
So xy belongs to either the converse of P or the converse of Q. These are equivalent. Hence, these two sets are equal. Is it clear?
Yes.
Look, there was no point to change union to intersection. No. And as a corollary of this lemma, I can prove that this operation, that of conversion, this operation is, as they say, monotonic. It is monotonic. What does it mean? That means that if P is a subset of Q, then the converse of P is a subset of Q, of the converse of Q, that is inwards. The converse of greater relation is generally greater, or at least not smaller than. Is it clear?
Yes, can we say that the converse of P is also a subset of Q?
Uh, under which assumption?
Because the converse doesn't change the set, but it only.
If P is a subset of Q, then the converse of Q is a subset. The converse of P is a subset of Q. This statement.
Yes, exactly.
Of course, it is not true. Assume that we have a pair 1, 2, which comprises our relation P. So P consists of one pair. Clearly, this is true, but this is not true. Is it clear?
Yes, clear.
So we should reorder. We should reorder elements in both P and Q. Okay. So how can we prove it? It is very easy. The best way to do so is to recall that P is included into Q if and only if we know, or at least we should know, that P is included into Q if and only if the union of these two sets equals what?
Is equal
Q.
to Q.
Exactly. But equal sets behave identically. So the converses of the left-hand side and the right-hand side must be identical. Is it clear?
Yes.
But according to our lemma 1, the left-hand side is just P conversed union Q conversed. And this equals Q conversed. So what do we see? The union of these two sets equals one of them. Hence, the converse of P is a subset of the converse of Q. That's all. Is it clear?
Yes.
Yes.
So just memorize this fact. If something is smaller, if P is smaller than Q, then the converse of P is smaller than the converse of Q. So this operation is monotonic. Aha! But what about composition? Let us put composition into our play. So we have the following theorem. Let us call it more solemnly a theorem, theorem 2. So we have the following properties for composition. The converse of the composition equals the composition of converses, and the order is also to be changed. Is this idea clear?
Yes.
And the second one, this is about associativity. Assume that we take this composition. We, I'd say, multiply for composition. If I multiply R by P multiplied by Q multiplied by P, you know, everything is from the right to the left here. Then I will obtain the same result as I first multiplied R by Q and then the result by P. Is it clear?
Yes.
Yeah.
I have already said you that I have already told you that mathematics is by far and large an art of analogy, of similarity, of seeing similarities, may be very subtle in apparently different areas, subjects, topics, statements, and so on. Have you already had matrices?
Yes, and geometry.
Mm-hmm. Do you know what is a transpose of a matrix?
Yes.
Matrix transposition.
Yes. Switching the columns and rows.
Aha! Exactly. But now look, assume that we have two matrices. Assume that these are matrices, say, of size n times n. But it doesn't matter. So assume that these are such matrices that this product makes sense. A multiplied by B. What is the transpose of these two matrices of the product?
B transpose times A transpose.
Look, this is very similar, isn't it?
Yes.
And after all, what is the double transpose? What if we take a transpose of the transpose?
It's the same matrix.
So these are quite similar. And of course, the product of A and B multiplied by C is the same as this product. Interesting. Is it clear?
Yes.
Aha. And even more interesting, we have already had the same stuff for strings. Do you remember strings?
Yes.
Let str be strings. For strings, we had two operations. Reverse. Do you remember this reverse operation?
It's reverse, comma, append.
You will have a string x1, x2, xn, then the result is a string xn, xn minus 1, and so on. Do you remember this operation?
Yes.
What is the double reverse of a string?
The same string.
But do you remember string appending operation, concatenation, gluing two strings together?
Yes.
What is the reverse of this string?
The append of the reverse.
Of T, the order has been changed. No, assume that here we had x1, xn, y1, ym. So here we will have ym, y1, xn, x1. Do you agree?
Yes.
And moreover, we proved that up of S and T and R equals up of S and up of R and T. Is it clear?
Yes.
So we have some similarity between these things. But now, let us prove this theorem. I shall need a little bit more space. So for the first point, AB belongs to this composition. What does it mean? That means that there exists some intermediate point C such that we have, excuse me, this is the converse. That means that BA belongs to P composition C. P composition Q. Is it clear?
Yes.
What does it mean? That means that there is some path going from B, first by Q, then by P, and leading us to A. Do you agree?
Mm-hmm.
Don't you?
Yes.
Mm-hmm. So then there exists C such that, please be careful, BQC, what is written last, acts first. We shall see why it is so later. So BQC and CPA. Interesting. What is my next step? My next step is to reorder these things. So there exists C such that C, Q converse B, and A, P converse C. Is it clear?
Yes.
Then let us do some logic. Something X and Y is logically equivalent to Y and X. So it is logically equivalent to this thing. A P converse C and C Q converse B. Ha! What does it mean? That means that there is a path from A to B, with an intermediate point at C. With an intermediate point at C. Aha! So that means that AB belongs to what? To this composition. Is it clear?
Yes.
As a result, this set equals this one because they consist of the same pairs. Hence, they consist of the same elements because every element of such a set is a pair, it is a binary relation. And now let us finish the proof of this theorem, proving the second claim. The second claim assumes that AD belongs to this relation P, to this one. Here it is, the left-hand side. Aha! What does it mean? That means that there exists some intermediate point C such that B, A R B, and B this composition D. Do you agree?
Yes.
Let us unfold this thing. What does it mean? That means that there exists some intermediate point C such that BQC, please notice that what is written last acts first. First by Q, then by P. Does this part depends on C? Does the left term depends on C?
No.
It doesn't. So that means that we can move this quantifier out. You know, there exists X, there exists C, such that today is Thursday and C is even. This is equivalent to the following statement. Today is Thursday and there exists such C that C is even. So I can freely move it out of the bracket because this part doesn't depend on C and obtain something like that. Aha! Another logical operation. I know that in this conjunction I can freely regroup statements. I can reassociate this order, I can regroup them. And moreover, I can change the order of these two quantifiers. It doesn't matter whether there exists B such that there exists C, or there exists C such that there exists B. So I may obtain ARB and BQC and finally CPD. Is it clear?
Yes.
Then look, does this part depend on B?
No, it doesn't.
No, it doesn't. That means that I can move this quantifier into the bracket because this part doesn't depend on B. So there exists C such that there exists B such that ARB and BQC and CPD. So here I have something like our definition. That means that there is a two-arrow path from A to C with a change point at B. So that means that AC belongs to the composition of R, first R, then Q. And finally, that means that AD belongs to the composition of two relations of QR and then P. Hence, this set equals this one because they consist of the same elements. Is it clear?
Yes.
So we have proved this theorem, and now let us finalize our today class with an example. It is a little bit informal. Okay, let A be a set of males. Let XPY means that by definition XPY means that X is a son of Y. So this relation XPY is the relation of a son to his father. Is it clear?
Yes.
So let us interpret some algebraic operations in layman terms, in terms of being a father, being a brother, or whatever. What does it mean that P converse Y? What does it mean? Or YPX? What does it mean for X? How does X relates to Y?
X is father of Y.
Yeah, X is the father of Y. So if you take the converse of being a son, you will obtain the relation of being one's father. Is it clear? X, P composition, P, Y. What does it mean?
That exists on C
There exists some intermediate point z, such that x pz and z py. So there exists some z, such that x is a son of z, and z is a son of y. But how is it possible? There is someone in between x and y in this sonhood relation. Who is z to x?
The father of X.
Father of x, but son but y. And now who is x in relation to y?
The grandchild.
Exactly. He is a grandson of y. And what about this one? What does it mean? So there is some z such that x, there is an arrow labeled with p converse from x to z, and from z labeled by p to y. Or equivalently, that means that z is what? How is it possible? What does it mean? He's a common son of x and y. How is it possible? How can one have two fathers?
They are the same.
Of course, in a so-called traditional society, that means that x and y are the same man, and z and this man has a son. X and y are equal, and x has a son. But of course, nowadays there are quite strange combinations. Say, you may think of them as a gay pair with a common son. What do you think about that? It is despicable, of course, but nevertheless, why not? And what about this one? What about this relation? What does it mean?
X is the father of Z.
There is some z. First of all, let us simplify it. There is some z such that x p z and z p converse y. Do you agree? Or equivalently, x p z and y p z. So x p z and y p z. That means that x and y has a common father. What does it mean? When X and Y has a common father?
They are brothers.
It is not the only option. What is another option? They are brothers or
They are
they are equal.
the same person. So
Of course, it is
they are equal.
well possible that X and Y are the same person, and every person has a father, of course. So this thing is not needed here. Is it clear? So from this example, we see that binary relations allow us to describe various things. Say, kinship relations. You can add some other relations, say, being a husband and a wife, and so on. You can use this formalism of binary relations, say, to describe kinship. Is this idea clear?
Yes.
And even more so, this formalism is very expressible for mathematical needs. We will use it to introduce and formalize, that is, functions, bijections, orderings, and so on. Do you have any questions?